let's work some problems from section 5.1. So I'm just going to work out, well, I guess 4 problems, some with multiple parts to them. So I'm going to start with problem 3, because you have problems 1 and 2 assigned to you in the homework. Here, for each of these vectors x and y, we are going to find the projection of x onto y, and then we're going to verify the directions of these, that the projection p and x minus p, and this was the z that we talked about in our construction of the projection, that p and z are actually orthogonal to each other. They're actually perpendicular. So let's just work through this. Remember our formula for p. P is equal to the scalar product of x and y divided by the magnitude of y squared, or you could write this as y transpose y as well, times the vector y. So notice here that this is a scalar over a scalar, and we're going to multiply y by this number. So we work on A. Here we need to find out what x transpose y is. We're just going to take the inner product, so 3 times 1 plus 4 times 0. 3 times 1 plus 4 times 0. And hopefully it's not too hard to see that is actually equal to 3. Magnitude of y. Technically, magnitude of y would be the square root of stuff, but since we're squaring it, we don't have to worry about that. So magnitude of y squared is, we take 1 squared plus 0 squared. And that is a 1. So our p, we're going to take x transpose y on top, so that 3, divided by magnitude of y squared, which is 1. And then we're just going to multiply that by y. And remember, y is 1, 0 transposed. So we're just going to multiply 1, 0 by 3, and we get the vector 3, 0 transposed. Of course, we also need to check that that when we take x minus p, that is actually perpendicular. So what is x minus p? X is 3, 4. We're subtracting p, which is 3, 0. And that difference, well, the 3's cancel each other out. We get a 0 there, but then we're left with a 4 here. And are these two orthogonal? How do we test if something's orthogonal? We take their inner product. We take their scalar product. So maybe I should put p transpose times x minus p. So we're actually transposing the transpose, so we're actually taking 3, 0 times the vector 4, 0 transpose. This is 3 times 0 plus 0 times 4. And everything gets multiplied by 0 anyways. So we do get 0. That means p and x minus p are orthogonal to each other. And of course, if we add those together, we get x, which is what we wanted to have happen. What about b? Do the exact same thing. X transpose y. This time it's 3 times 1 plus 5 times 1. We get an 8. Magnitude of y squared. Now we have 1 and a 1, so 1 squared plus 1 squared gives us a 2. P in this case is 8 over 2 times our y in this case is 1, 1 transpose. So we're going to multiply by 4. We have 4, 4 transpose. X minus p. Remember, x is 3, 5. P is 4, 4. So x minus p, we have a negative 1 and a 1 transpose. And of course, we're going to check that these are actually orthogonal. So taking the scalar product of p, which is 4, 4, with x minus p, which is negative 1, 1 transpose. When we put those together, we have 4 times negative 1 plus 4 times 1. So negative 4 plus 4 gives us a 0. Now we work on C. Do the same thing. We're going to take x transpose y. In this case, we are working R3, so we have more stuff going on. We have a 2 times a 1. We have a 4 times a 1. And then we have 3 times 1. 2 plus 4 plus 3, we end up with 9. We also need magnitude of y squared. Well, that's just a 1 squared plus 1 squared plus 1 squared, which is 3. So p in this case, we have 9 over 3, just those two numbers, times our y, which again is our 1, 1, 1 transpose. And so 9 over 3 is 3. We end up having to multiply all the 1's by 3's. So our projection is 3, 3, 3. Of course, now we need to look at x minus p. X in this case was what? It was 2, 4, 3. And we're subtracting 3, 3, 3. So 2 minus 3 gives us a negative 1. 4 minus 3 is 1. And then we get a 0. And so the scalar product of these two things, which I'm not going to write them out again, but we're just going to take the scalar product of these two vectors. We have a 3 times a negative 1. We have another 3 times a 1. And finally, we have a 3 times a 0, which I didn't really have to write that one down, but I did. Negative 3 plus 3 is a 0. They are orthogonal to each other. Then finally, D. Exact same kind of concept. X transpose y. This time it's 2 times 1 plus negative 5 times 2 plus 4 times negative 1. If we add all those together, it's a little bit more involved this time, but we get a negative 12. Then we want the magnitude of y squared. That'll be a 1 squared plus a negative 5 squared plus a 2 squared. Or wait, sorry, taking numbers from x for a second there. No, we have 1 squared, we have a 2 squared, and then we have a negative 1 squared. Yeah, don't mix up your vectors. What do we get here? We get a 6. And then our p, we're going to take this negative 12 over 6. We're going to multiply it by our y, which is 1 to negative 1 transpose. Negative 12 over 6 is a negative 2. So we're going to multiply everything by negative 2. We have negative 2, negative 4, 2. Note that this projection is actually in the opposite direction from y, because we did get our scalar projection in front was a negative. But it still is a multiple of the vector y. It's still just some number times y. And that's really what we're looking for. X minus p. Here, our x was 2, negative 5, 4. Our p was negative 2, negative 4, 2. And so when we do all this subtraction, we get what? 4, negative 1, 2. Now, are these orthogonal? At this point, hopefully you believe me that they will be, but I'm going to work it out anyways. We're going to just take the scalar product of these two things. We have negative 2 times 4 plus negative 4 times negative 1 plus 2 times 2. So negative 8. This becomes a positive 4, so negative 8 plus 4 plus another 4. That all cancels out to give us a nice 0, which is what we wanted. Next, we have a problem that really doesn't seem to have anything to do with vectors in the first place. We're going to find the point on the line y equals 2x that is closest to the point 5, 2. So maybe a picture is in order here. So we want to draw a line. Let me go through the origin. This is going to be the line y equals 2x. They made it a little bit too sloped there, but that's okay. We're going to have a point that's 5, 2, so somewhere maybe around over here. And we want to find the point that's on this line that's closest to this point. Now, from geometry, we kind of already have the idea that if we drop a perpendicular from this point to the line, the point at the bottom, at our base of this perpendicular, is going to be closest to this point. Any other point is going to be a little bit further away. So we need to find out what is the point that is at the end of this perpendicular. And we're going to use vectors to do that. We're going to think about this point here as actually being the vector 5, 2. And we're going to try to find a vector along our line that we can project onto. So if we can find a vector on here, then the projection of the vector 5, 2 onto that vector there should be the correct vector and give us the correct point here. Well, what kind of vectors are actually on the line y equals 2x? Well, we just need to find a point on the line y equals 2x. And using that slope, that's pretty easy. We can find a point, say, plug in 1 for x, we get 2 for y. Actually, that kind of lines up nicely because it is parallel to the 5, 2 that we have over here, but it has the same y coordinate. So we have a point 1, 2. Or in other words, we have a vector 1, 2 that follows this line. And we want to project 5, 2 onto that line, onto that vector. Let's name these. Let's call this one, I guess to fit with our notation from before, we'll call that one x. We'll call this one y. These are not the coordinates x and y. These are vectors x and y. Make them bold if that was easy to do. But not really going to cause us any problems. We want to find the projection of x onto y. So remember, we just take x transpose y. Technically, we're working with our column vectors here. So this is 5, 2. This is 1, 2 transposed. If we work that out, well, 5 times 1 plus 2 times 2. 5 plus 4 gives us a 9. We need the magnitude of y squared. Y is 1, 2, so we have 1 squared plus 2 squared. 1 plus 4 gives us a 5. So finally, our projection is going to be 9 over 5 times y, and y is 1, 2, or 1, 2 transpose. So this is our vector. This is the p, and p is the vector from the origin to this point here, the point that we're looking for. So the coordinates of that point are literally just the numbers that we have in this vector. We have to move the 9/5 into there, but our first one is 1 times 9/5, so 9/5, and then 2 times 9/5, or 18/5. So maybe not a number we would have expected, but that is actually the closest point to the point 5, 2 that is on that line. Here is a similar problem. Again, we have a point and a line, but now we're asking what is the distance from the point to the line. So again, let's draw our picture. And they gave us a kind of a weird way of writing this out. So 4x minus 3y equals 0. If we solve for that for y, we're going to get y is equal to 4/3 x. So again, just a multiple of x. That's not really required. And actually, in problem 6, they gave us one that does have plus something at the end of it, but we're just keeping it simple right now. So we have a line. So let's say this is our line y equals 4/3 x. We have a point. In this case, we have 1, 2. That actually lies a little bit above our line. Maybe draw it up here. And we want to know how far is that line, how far is that point from the line? Well, again from geometry, the idea of how far a point is from a set here being the line y equals 4/3 x, is just how close is it? How close can we get to x? Well, the shortest distance, like we did in problem 5, was just drop a perpendicular. We can drop a perpendicular, and we're really looking for what is that distance of that perpendicular to the line. And I'll leave that out just because it's kind of clutter. And kind of wish they gave us a point that was a little bit further away from the line so it'd be a little easier to work with. But this point really is pretty close to the line. But we're doing the same thing. We're thinking of 1, 2 as a vector. Maybe I won't draw it this time just because to not clutter it up too much. We want another vector along our line. In this case, what would be an easy one? Well, if we picked x equals 1, we're going to have fractions involved. Let's say instead we'll pick a longer vector where we pick x equals 3 to get rid of the fraction, and we'll work with the point where we have 3 for x and 4 for y. That'll be a nice number for us to use. And now we're looking at what is this projection. Again, let's call this point x, and we'll call this point y, just so I can write them down easier. So we're looking at the projection, so we start with our scalar product, x transpose y. We have 1, 2, multiplied to 3, 4 transpose. We have 1 times 3, plus 2 times 4. 3 plus 8 gives an 11. We need the magnitude of y squared. That's going to be 3 squared plus 4 squared. Well, this gives us 25. Or essentially 5 squared, if you remember the 3, 4, 5 triangles. We use those quite often when we don't want to end up with square roots in our problems that involve the Pythagorean theorem. But yeah. Still we're keeping the square on it this time. Our projection, we're going to take this 11, we're going to divide by the 25, and we're going to multiply it by y. So we're going to multiply it by 3, 4, transpose. Or really what we can say here is that we have the vector 33 over 25 and 44 over 25, transpose. Because what are we going to do now? Because we're not really interested in p. We're not really interested in what is the distance from the origin to the base of this perpendicular. We're really looking for the length of that perpendicular. And the length of that perpendicular is the vector x minus p, the vector that is perpendicular to the vector p. So we are going to have to subtract this vector p from our original vector 1, 2. So what is 1, 2 transpose minus this a little bit cumbersome 33 25ths, 44 25ths transpose? Turns out it's not too bad. 1 minus 33 25ths is actually negative 8 25ths. And 2 minus 44 25ths is 6 25ths. And what we want is this length, the length of that vector. The length of that vector, we have a square root. We're not squaring it this time. We have negative 8 25ths squared plus 6 25ths squared. And ultimately, this turns into the square root of 100 over, I'm just going to leave it as 25 squared. But 8 squared plus 6 squared gives us 100, so it works out pretty nicely there. 100 is 10 squared, so we can actually cancel out the square root. This is 10 over 25, or if we cancel a 5, we get a 2/5. So that distance there is only 2/5. So like I said, it's pretty close. It's not even 1 unit away. It's only 0.4 units away. So pretty close to the line. But here, using these projections, we were able to find that distance with not too much trouble. It'd been a lot more trouble if we actually had to go in and do all the geometry ourselves. But this is pretty straightforward. We find that projection, we find out what the actual orthogonal part is, and then we find the length of that. In this last problem, and this is a multi-part problem, but it's actually a very important problem because we're going to work with planes in three-dimensional space. So we have some plane. I'm going to just denote it by a rectangle here, but you can imagine this sitting. Imagine actually being a rectangle sitting in three-dimensional space somewhere at some orientation. And we're going to think about how we can actually get an equation of this plane. And that's going to be kind of important for you in problem 10 on your homework, because there you're going to actually have to start with the equation of a plane and extract the relevant information to solve a particular problem. I'll talk about that one in a moment when we get actually define a few terms here. So how do we actually work with this? Well, we're going to assume that we know a point in the plane. We're going to call that point P0, or P0 sometimes we refer to it as. We're going to say it's the point x0, y0, z0. It just has those coordinates. If we have another point in the plane, call this one P, and it has coordinates x, y, and z, so these are just going to be the x and y and z that we're allowed to vary around on our plane, and we're going to try to find out all the points P that are on the plane. We can form a vector from P0 to P. This is a vector in the plane. We can imagine that there is a vector that sticks out of the plane that is perpendicular to every other vector that's in the plane. So it'd be perpendicular to this vector here, from P0 to P. Such a vector is called a normal vector, or specifically a normal vector to the plane. Usually we use an n. A lot of times people use a lowercase n. Here they're using an uppercase n, but we're going to call that vector n. And if that vector n is some ABC, make that here, ABC, and this is actually in a vector now, then really what we're saying is what points x, y, z give us vectors in the plane that are perpendicular to ABC. Well, the vector from P0 to P, which we can actually write as P0 to P0 P with an arrow over it, we can find this by taking the difference between the coordinates of P0 and P. We take the terminal point P and we subtract the initial point P0. So we have x minus x0, we have y minus y0, and z minus z0. We're going to put this as a column vector now because it is a vector. We don't really want to think of P0 and P as vectors. It's not really too useful to do that in this context. But we're asking which points P make this vector here orthogonal to n. So what is the inner product, or the scalar product of these two vectors? So I guess this vector transposed times n. Well, we're just going to take x minus x0 times a, or I'll put the a out in front. And then we have b times y minus y0. And then we have c times z minus z0. And for this to really work out, we want this to equal 0. We want these two vectors to be orthogonal. So really, this is what our equation becomes. If we have a so-called normal vector, ABC, then we can stick those A, B, and C in front of these differences, and get an equation for our line. Or, not a line, a plane. An equation for our plane. So, that's what we have here. We have a given vector in, that's our normal vector, and we have our point P naught. So in A, we just take 2, that's the first coordinate of in. Then we have x minus 0, because the first thing in P naught. Do the same thing with the second coordinates. We have 4 times y minus 0. Then we have 3 times z minus 0. And that's going to equal 0. Now, we probably want to go ahead and simplify this. There's no reason to leave the minus zeros in there. So I'd write that as 2x plus 4y plus 3z is equal to 0. Same kind of thing with b, though in this case p naught is not 0. So we'll actually have some stuff in there. We again take the first component of in, which is negative 3. We multiply that to x minus 4. We have a plus 6 times y minus 2. And then we have a plus 2 times z minus 5, so plus 5 is equal to 0. Again, we probably not want to leave it in that form, though you can. There's no reason we can't. But I would go ahead and pull out all the minus 3x plus 6y plus 2z, and then I'll move all the other ones to the other side, because we'll have a plus 12, we have a minus 12, and then we have a plus 10. And when we combine those and move them to the other side, what do we get? Well, we just end up with a negative 10 on this side. And that's usually how people would write it. Finally, C. Well, now our normal vector is 0, 0, 1. Our point is 3, 2, 4. So we do the same kind of thing. We have 0 times x minus 3. We have another 0 times y minus 2. And then finally we have a plus 1 times z minus 4. Of course, this one you definitely want to simplify. Anything times 0 just goes away. And then we just have the 1 there that we don't really need to worry about. So we have z minus 4 is equal to 0, or in other words, z equals 4. A nice simple equation of a plane. But that is how we actually find the equation of a plane. This is really the way that you always will want to find the equation of a plane. If you've taken Calc 3, you've seen this before. If you haven't taken it yet, we do this kind of stuff in Calc 3 all the time. Or maybe not all the time, but when we talk about tangent planes to surfaces and that kind of stuff, this is a very important technique. And part of some of the stuff you do in Calc 3 is how would we find such a normal vector. It's not always the most obvious thing. If you remember the cross product, if you've ever heard of that, that's one of the techniques that they use to actually find these normal vectors. But we're not going to be working with the cross product in linear algebra. Mostly because it doesn't generalize to anything other than R3. So, in your problem 10, you are going to kind of go the other way. You're going to be given an equation of a plane, and you want to find the normal vector. So you're looking for these coefficients of x, y, and z. Those are going to be your components of your normal vector in. Make sure they're all on the same side of the equation if you do that. So don't move z to one side and the x and y to the other side and then take the numbers there, because some of those will then have the wrong sign to them. So here, if they're all on the same side, we can just read off from here 2, 4, 3, and that's the normal vector here. Technically, we could go ahead and say maybe divide everything by 2 or multiply everything by 2. We'd have a different vector in that case, but it will still be parallel to the end that we have here, and it'll still be useful for what we would need to do in that problem. So if you have any questions about that problem, and and you don't get the answer from the text anyways, you can always look in the text and see how they explain things if you don't like my explanation. But you can also come to my office hours and we can work through it a little bit. So, but that's all I have for now. And again, if you have any questions, you can always come to my office hours and see me then. So, see you later.